Welcome, everyone. My name is Daniel. I'm the secretary IEEE Magnetic Santa Clara chapter. For today, we have an event of more than 80 people registered. We're all here for Mr. Turguy Göker's presentation. Turguy is the director of Advanced. He has been in the tape industry for over 30 years as a magnetic recording technologist, specializing in the signal processing technology, developing LTO drives, media, and tape formats. He represents Quantum in LTO organization and since 2015 has been the chairman of the board for Information Storage Industry Consortium. Turguy was a key member of an R&D team that was responsible for the original LTO project, collaborating with HP and IBM in formatting today's LTO organization and tape technology. The Turguy has more than 50 patents in the tape technology field. As an LTO researcher, he was selected for the Technology Hall of Fame with Seagate, Certens, and Quantum. So now I'll pass the mic to Turguy.
Good evening, good morning, good afternoon, everywhere else in the Zoom area. Today, I will be talking about tape technology and where is it going, especially regarding the increasing areal densities. Now, we're nowhere near where hard disk drives are, but when you consider it's removable media, 5-micron thickness, less than that actually, and moving at 5-6 meters a second, maybe 10 meters a second per second, over rollers and guides and everything. And yet you have to control and read your data with multiple different channels, all dimensional controls that has to meet certain guidelines and be able to support what we call nines as the durability metric these days of minimum 11 nines. It becomes challenging. The presentation will go over tape roadmap, and that covers LTO or roadmap, and also I will go over 7, 8, 9, where we are today and where we'll be going down the road, next generations. And I have a few slides on tape technology, meaning when you look at the tape drive, how does the user data gets written? And how do you detect this thing? What's the core technologies? I won't go over the mechanism aspect of it, simply stick with digital signal processing, ECC formatting, and error rate type information. What does that really mean? And later the slides, I will be going over database metrics. And when I say database metrics, we collect massive amounts of data from drives. And so I have data that collected over the years from LTO 7, 8, 9, 10. At 10, we don't have the data yet. We're just in testing. But those 3 generations, we have data that represents from exabytes of writing, exabytes of reading. People have written overall 20, 30 exabytes of data and read more than that. So this is millions of tape loads, billions of meters of tape motion. So when I talk about the error rate, Pareto's and information, it's based on that type of data. I'll try to summarize those things. And finally, I'll be going over technologies that we have developed and we're investigating even more, which is called erasure coded LTO tape technology. Erasure coding is something we all use. We all know how it's done, but with tape, it's kind of new. So we'll go over that. So next slide is an overview. Basically I'm not going to read this whole thing. What it's trying to say is to make capacities higher and higher, just like the disk drives, we have to make 2 things change. One of them is length of tape. You have to put more tape in the same space. To do that, you have to make thinner tape, thinner substrates, and that's one variable. The other one is areal densities. You got to keep increasing areal density. As a result, for tape, the thing that you want to move, your substrate, gets thinner and thinner, and your tracks written bit dimensions get smaller and smaller. That introduces challenges, given the fact that this has to operate in an open environment over a wide range of environmental conditions. So with those things and with removability, you write in one tape drive, you take a thing 6 months later, you put them in another tape drive, you have to append it, yet read it with some other tape drive later on. Those interchange requirements from drive to drive, media to media, open environment, debris conditions, it complicates the things, especially as dimensions get smaller. Yet we still have to manage and maintain, quote unquote, that 11 nines durability. Now that's a big number, okay? And so I'll go over that because there's a lot of assumptions has to go to generate that number. It's a number that is published by AWS that if you write your data into Glacier, they keep it with that type of reliability. And they use copies and erasure code technologies to do that. Finally, we also use erasure coded tape technology, which is it's a unique two-dimensional erasure coding. I will go over that because erasure coding with tapes don't match good because you got, unlike disk drives, you want to get a file, everything is online, available, rotating. You want to get a 100 meg file, 100 gig file. Now you need to find 6, 7, or 10 different tape and load them into 10 different drives and read that thing. Well, here's the catch. For every 100 tape, there's one tape drive. So it's not like you got tape drives laying around available for you. So it makes this thing challenging. So we'll go over how we did that. This is the magic, everybody knows this, InSIC roadmap. X-axis is years, Y-axis is areal density, gigabits per inch square, and LTO tape and earlier tapes are showing 1995. I was working on them back then. And if somebody was to ask me, 30 terabyte tape drive, back those days, I said, are you crazy? Yet we are here and it is reality. And I actually tested massive amounts. I wrote nearly 1 petabyte data and read them. So it's like, it's reality, definitely real. Next slide is I took the same data for tape only. I wanted to give you a perspective of what we're looking at in reality. What does this really mean? Because in previous slides, we basically increased linear densities year after year. Where is it going? I mean, it can't just keep going. What does that really mean? Areal density is related to track density and linear density. That's it. So x-axis is linear density, kilobits per inch. Y-axis in log scale is track density, kilotracks per inch. Densities, these are in real world, we have number of tracks because we got some spatial space that we have to deal with. Over LTO1, track pitch was, I have to say, in nanometers, because these days we deal with nanometers, it was 27,500 nanometers. You go to LTO9 is 1,156 nanometers. You have to think about, wow, where we were, where we ended up getting. So it's about the same type of tape. Yes, tape was shorter, but it's not 10 times or 20 times. It's some reasonable amount. As you notice that there is a increase in linear density along with track density each generation till about LTO 9. 8 and 9 was a little bit changing. There's a reason for that. Back those days, we had margins in the system in SNR, and our tracks are so wide and readers are big that we can do that. And we were also improving the media characteristics, media particles, and magnetic characteristics. So that was doable. But when you get to that red line, you're going to be operating in that yellow triangle. The hypotenuse type of line is established by InSIC. InSIC said, you know what? If you were to increase linear density and track density, that's the most likelihood line you're going to follow. The other one, vertical, if you don't change the linear density, you just rely on track density, that's the direction you're going to go. So somewhere in that zone, we're going to be operating. Next slide. If you want to take a look at what does these bits relate, what do they mean? I can't show you LTO 1, 2, 3, 4, 5. They will be at this scale way off the chart. It's not possible. So I showed you 6, 7, jumped 8, 9, and where 10 is going to be like. And these are the number of tracks, number of KPBIs, and you can see everything getting smaller and smaller. So you have looking at LTO 10, 30 terabyte, operating at 400 megabyte per second, SAS and Fibre Channel speeds. And there's no downward compatibility. It's a tilted head, and I'll go over that thing. With tilted head, you can't read standard vertical written tracks. You just, same head, cannot do it. And worm and encryption and LTFS is always available for us. Next slide, please. Okay, this is now, I'm going to go over at a high level, how do you detect, how do you write data? So let's go to the next slide. This is your basic channel. You got a user data, comes into tape drive. First thing it does is Reed-Solomon encodes the data. It does it in two-dimensional, two different ECCs. We call them C1 and C2. The reason for that is you want to protect your data longitudinally and across in an area, a rectangular area. So you need two different dimensions. Then it doesn't run length limited encoding. The reason for that, you don't want too many ones or too many zeros in a row. After all, when you're reading this thing with tape moving at speed variations and everything, you want to be able to detect your bit position. And if you have long length of ones or long length of zeros, it makes PLL, phase lock loop, to be very difficult, timing recovery. And then precoder, to me, that's like, is a special thing I never really understood, be honest with you. It has to do with Viterbi detector in the system not to have error acceleration. If you have a small bit of error, it doesn't cause additional errors that causes bigger errors where it blows the C1 or C2 ECC, mainly C1. Then you have a writer, you write this thing to tape and you read it. Read path is the same during read only or read while write. Tape drive does read while write. So you do the same thing. You synchronize data, you inverse precoder, do the decoding RLL, you get the C1 if you're writing only, or C1, C2 if you're reading, then you get your data. So we'll go over the next one is a little bit different. Next slide, please. And this is, you look at a tape, LP0, beginning of tape. That's where the thing attaches to the reel. 1,000 meters later, you get the LP7. That's the other end. It's wrapped up at the very end. And there's a leader pin, and that can get routed into the drive, attached to the drive reel, and then you got reel-to-reel motion. You break that thing into these different regions. These regions are basically identified by tape linear position information. Where do you get that? It's written on the tape. There's 5 servo zones. These are like 80 microns wide zones. They have chevron patterns. I didn't describe that in here. Look, you can find that in Wikipedia. There are chevron patterns where you, depends on where you are on the chevron pattern, you know which lateral position you are. And guess what? We encode that chevron position longitudinally, put ones and zeros there with CRC check, such that you know where you are on the tape longitudinally. They define your zones. LP0 to 1, don't do anything zone. That's like dummy zone. 2 to 3 is your calibration housekeeping. 3 to 5 is your actual data. 6 to 7, don't do anything. And that's your zones. There's 5 servo zones, isolates 4 data bands. These are your data bands. That's where your data goes. You write your multi-track data and wraps everything. Keep in mind, more tracks. If your head channel number is 32, which is today, that means more wraps. That means more times you're going to pass over that tape. You have to think about tribology, the wear, the bridge generation, all that stuff. So all that has to be managed. Next slide, please. I'm going to skip over this thing. It's pretty explanatory. Basically, there's right driver, there's preamp, there's an analog signal path. The white is analog domain. That's your pure analog domain. Preamps, analog filters, all that stuff. Things that we all have studied. The purple is your bit domain. You have to get those analog signals sampled. You have to oversample them and then find the right sample with PLL. With this ITR, time in recovery, you get your ones and zeros. Then that gets fed into Viterbi detector, and that tells you it recovers data. And then after that, you feed it into ECC, C1, C2, ECC. Next slide, please. I have to keep myself on time here, okay? How's your data gets written on the tape? White box is your user data. That's what you give to the tape drive. It takes the data, it chunks it. In this case, if you're using LTO 9 and 10, each chunk is called dataset, is 10 megabytes. So don't give less than 10 megabytes and expect it to write, just like gonna crash the tape drive. You basically take the data and you break it into, in this case, 64 different chunks. I'm showing you only one of those 64 chunks, okay? Then you take the user data. First thing you do at Reed-Solomon, in this case, 192.24 ECC. Data is 168 bytes. Parity, 24 bytes. It's a long code word. Very good. High efficiency, high protection rate, long code word. It ECCs that thing, generates 912 columns of C2 encoded code word. Then it adds headers to each one of the rows, okay? Because you need to know metadata. That's your metadata. You don't write that. And then once he has the metadata and the C2 ECC user data, then what it does is it generates C1 ECC longitudinally, rows, 192 rows. So I got 100. So basically, I have bytes of one line. This represents one of these lines, indicated by the blue arrow, one of those guys. I got 192 of them. Then what it does is it takes every byte, generates code words, and then it interleaves code words. So when you have a defect on the tape, you don't get an error immediately. You blow your C2 ECC, C1 ECC. No, because of interleaving, it prevents everything. Next slide. Then once you have these things, it also does C2 based on C2 ECC. It spreads them such that they're apart from each other. So you got longitudinal, lateral, two-dimensional, what? Interleaving. That's what this power of tape drive is. Next slide. I'll show you my perspective, because I didn't design this. This is LTO 9, Jason, and how a tracking loop works, overall tracking loop, because LTO 9 does dimensional stability, azimuth control, and tracking control. You got 3 different actuators. 2 of them are physical linear actuators. The third one is attention control. So you basically, what you do, you calibrate. If you're working with, how many of you worked with LTO tape drives? Well, besides you guys. Anyone familiar with it? Okay. Basically, you put a cartridge in the drive, LTO 9, it calibrates. Before you do anything for 20 minutes, 30 minutes, it goes back and forth. That's some magic. It's basically measuring these things. And it puts that information in his CM someplace, okay? That's his like metadata, servo metadata. Then when he's tracking, he uses the track reference servo heads to close the tracking loop, skew reference, skew actuator, close the skew actuator. That's the tracking is up and down, skew is azimuthal. And then he uses this data based on environmental conditions, uses tension to adjust the width of the tape. That's how it works. Works beautiful. We have massive amounts of data to show that. Next slide. Okay, so that's LTO 1 through 9. Right-hand picture there. Heads are vertical, servos are purple, the tape is orange, okay? You write tape that way. So you make sure it's all done, it's all controlled that way. LTO 10 got much smaller tracks. Things are getting smaller. Dimensional stability is much more challenging. You align 32 heads with 32 written tracks by somebody else in some other condition, and you're reading at your own condition that happens to be totally opposite, for instance. And how do you solve that problem? So each generation, it becomes difficult. Solution is called tilted head. Bob Biscaborn from IBM, I think he named it as Pizza Head. And we had that technology described 13 years ago in InSIC meeting that was published right there. And the original patent belongs to a guy from Quantum named Jug. I didn't met him, and he was on DLT. Back those days, I was on LTO. But we talked about his patent, his technique, although he didn't implement it. Later on, Bob saw the concept, and then they implemented their own, and it's called tilted, and that's what the technology is. Basically, you write things tilted, not azimuthal. Azimuthal, you write one direction, you opposite direction. This doesn't do that. Rather than writing things vertical, you write them with a slight angle. Then you measure the dimension of the tape with your servos. If it expands or contracts, you slightly change your tilt angle. Excellent. That's the technology. That's it going forward. That's why you cannot read older tapes with today's head. Next slide. Okay, 26. Okay, I'm going to talk about real world errors. Next slide. Okay, so there is Carl Watts, tape expert, user, Library of Congress. He published this. This is the link at LinkedIn. You can read it's a great write-up. He just basically wrote everything. I said, wow, Carl, thank you very much. I mean, this is great writing. We weren't going to say that much. You said it. That's awesome. I mean, just look at his description, why moving 34 petabytes shouldn't cost millions, but still does. Well, there's reason for that. First, the point that he's trying to make is we assume perfect condition. We assume drives all work. Files are intact, okay? You can read all the tapes. There's no contention, no ingest, nothing. But he says, hey, guys, the reality is when I'm trying to migrate this thing, my drives fail. Mounts, loads takes a long time. I've seen that, yes. Not every load, but when you start doing that migration, it does impact them. And fixities fail. Keep that in mind. Fixity is very important, especially with high areal density tapes. Script stall, resources saturate. So he goes, well, you have to do something else. So I gave a presentation at Library of Congress earlier this year, and we talked about similar things. So next slide. You may have heard UBER, user bit error rate. Super important. Without that, you can't have a tape drive. That channel that I showed you, that ECCs, all that interleaving is designed to make sure at those operating conditions, those track pitches, that reader widths and that magnetics and that speed, you can have one error unrecoverable in 10 to the 20 user bits read. That's it, not lower than that. That's your number, and we meet that. But keep in mind, that number assumes your errors are all random. That's key. If your errors are correlated, you got bunched error due to some condition, you can't use UBER, because if we had nothing but UBER in my lifetime, I would have never seen a tape error. Okay. So what the real world errors are, you've got human errors, lost or stolen tapes, you drop a cartridge, damages condition, so you can't load in. Tape getting cut and it can drop the pin. These are rare events, but they're not zero. When you're talking about 0.001% error rate, which is very low, that's still not 11.9. It's far away from 11.9. 5.9. Stresses. These days, that's very important. Built-in tape pack stress. You got hoop stresses and radial stresses, radial pressures. And these things could create uneven stress profiles in your layers, especially near the hub, because You got all those tape layers being pressed against an inner hub, and depends on if the hub is too strong, then it's going to impact the pressures on the layers. If it is too soft, it's going to create a different problem. It has to be optimized. And I think my colleagues, they're perfect at that. So those are important because when especially use the tape in a random access mode, you stop, start, you do a back hitch at 6 meters per second, you're moving. I measured this. I know back in LTO 4 days, measure that there's about 100 or 200 meters of floating tape. And then you decelerate, stop, reverse direction. What happens to that? So all those air has to bleed through and everything. So anyway, those are all real world problems. Other things, well, stagger wraps, I said, tracking at BOT, EOT, those are very difficult areas. It's challenging. It's doing a great job, but it is challenging. And media wear, as we increase areal density, especially with track density, without increasing head channels, your wraps increase, number of passes across the tape increases. Well, that affects the wear and tear. Next slide, please. 31, okay. Okay, what is this? Tape alerts. If you use tape drives, you know tape alerts. You don't know errors. Upper right corner, I describe you errors because we know. This data is from, massive number of, I think this is from 190,000 loads or 40,000 tapes, a lot of drives. So it's big data. I'm a data hog. I collect everything. At some point, they say, what do you do with that data? Well, we analyze, we find out, especially these days. In quantum, we use data for data analytics using machine learning algorithms and trying to do AI, apply AI, to look for big data correlations between events, time domain correlations. And we look at papers that are written by various universities, research that is done, and we see how can I apply those technologies? Is it applicable? If yes, how can I apply it to our application? So we categorize errors, those 6 buckets. You got drive error, load error, no error. That's awesome. And read error, servo error, write error. Okay. Now, when you have tape alerts on the x-axis, those are tape alert numbers. You can get them from SCSI pages. It tells you these descriptions, but I wrote them for you here. You can see which ones are which. Okay, so interesting thing is you have one tape alert, it can show you, it could be due to multiple different errors. Which one is which? Well, you need to learn that. As you collect the data, you can correlate which one goes with, oh, okay, I had that combination, is that so forth. That's not easy to do. That's part of our research is always trying to figure out, because people use tape alerts and we need to be able to say, hey, it's that, it's not that. Otherwise, what happens is people ask you questions, why this error, why that error, and you can become very quickly, you can become a tape expert. All you have to say, did you clean your drive? Did you check your environment? You're a tape expert. That's it. Otherwise, you get into deep explanation. So next slide. This one is x-axis tape sections. From 0 is beginning of tape, 80 is end of tape. It's broken into 80 different sections or 82 different sections in this case, I think. And there's y-axis is percent of errors. From a very large, well, there it is. 530 petabytes written data, 350 petabytes separate read, different read. This is physically reading. And 190,000 loads, 200 plus LTO9 drives, 20,000 media. I have the data. When we look at and characterize, where did my errors occur? It should be random. No, that's the point. And if you were to go and break these errors into groups of error categories, the one that I showed you before in the previous, drive errors, load errors, read errors, servo errors, write errors, look at the right-hand axis, 9s. Just translate those numbers into 9. You can add 9s if the errors are random. You cannot add them otherwise. You cannot multiply them. You have to convert them back to percentages and go back through the logs to calculate it. But if you look at it, it's not better than 4 9s. So you say, well, how do I get 11 nines? Okay. From that number, how do I use 3 copies? Okay, perfect. Look at this error profile. If all your 3 copies have the same error profile, can you add those nines? No. So what happens to your copies? They're corrupted. So you take a data, you got a couple drives, you generate your data, original data cartridge, and you generate the copy cartridges with the same drives. You should pick different. Well, I don't have a different drive. Well, I mean, that's where you need what is your goal? If you really want to go reach those big numbers that is published, you have to pay attention to them because that's the reality. Next slide. Okay, this is an eye chart. This is 4 different tape generations, X, Y, tape error position. And he saw that. I presented this morning. He goes, oh, most of your errors are beginning and end of tape. Yes, Daniel, you're absolutely right. Good eye. And that's what it basically says. So from generation to generation, it really hasn't changed. Next slide. And I'm not going to go over this. This basically tells the same story, repeats. Best you can get from a tape cartridge is 4 nines. If you want to use copy, you have to make sure you are not, you randomize your process. Next slide. Okay, now, what did we go from here? What do we go? Like, what does quantum do from here point out? What we have been doing is we developed back in 2012, 2015 years, a technology called two-dimensional erasure code because we knew the tape. We wanted to do something, and we said, how can we put erasure coding in the tape at the host level? Because we have it at the tape level. How can I do it at the host level? And so we came up with that technology because you couldn't really do erasure coding with tape because of the reasons that I mentioned to you. You want to get 100 meg files, you got to find 10 different drives. I only have 5 drives. How am I going to do that? Okay. Next slide. The system is called ActiveScale Cold Store. Now, we had the technology, but we didn't know how to do erasure coding at host level. That's different. That's like object, storage, magic, okay? But we acquired this company called ActiveScale from Western Digital. They had the magic. Well, we had this technology, we had the know-how. We said, hey guys, can you do this? They looked at it, they said, oh yeah, because the thing that we wanted to do, long code word ECC. You can't do that unless you have a hardware accelerator or you have some software magic. That's where their software magic came in. Basically, you have I have a different slide that describes to you, but every file is written to a different tape. So if you want to read a file, you load one tape and one tape only. That tape has that file objects interleaved and erasure coded with local parities. So each tape has a local parity. And now those tapes, you get a bunch of them, then you generate parity tape across the tapes. So you got one dimension across the tape per tape dimension individual. If you want to read a file, you just pick one tape. That's all. 99.99% of problems are related to one tape. So there's hardly, unless you physically lost the tape or it's totally damaged, shredded, you don't need to pick different tapes. You just use that tape alone. What we call that is a locally repairable tapes. You have that terminology in the disk world. You have locally repairable disk groups. You have enough parities in a group of disks that if there's a failure, you can repair it there. Unless that group is gone, then you need to rebuild it. Next slide. 5 minutes. Okay, so these are some of the clear metrics we have. Next slide. And basically, striping is different than what we're doing. Striping is you take a file, you stripe it across multiple tapes. You get some benefits, but your read speed is as good as your slowest drive, and that's always the case. And to get a file, you have to have all the tapes, all the drives, which gives a logistics problem of not having access to, because you got small number of drives, and at the time of you want to read that file, you need to have access to 10 clear drives that are not busy. How are you going to manage that? Not possible. We have addressed that. Now, we have overhead extra that these guys do. but it's only less than 6%. Why? Because we wanted to implement long code words. Actually, we did implement LDPC, rateless codes, to demonstrate this technology. I even used Qualcomm's Raptor Q code. Works really good. So the concept works good. With Reed-Solomon, we can get quite long code words that can be efficiently implemented by software that is less than 6%. Next slide. This is your tape errors and tape alerts map, a typical system on the right here, and what we're able to do with the ActiveScale. Because it's all buffered, everything, we can control the tape motions, tape underruns, tape utilization much better. Next slide. This is 3 different charts here. These are soft errors. Write mode soft error on the top left. Top right is read mode soft errors. Blue is like a large-scale legacy application. Green is our ActiveScale. So you can see that we have reduced the soft errors. What is soft error? You don't see that, but it is there, available to you with SCSI documentation. It's called ERPs, means drive fails to read something, stops, repositions, picks from the list. Oh, I should try this algorithm, and does that. Oops, I got to do another one. And where are they happening? How often they are happening? Those are soft errors. It means there's something wrong in that area that is trying to recover. So we are able to reduce the soft errors in both write and read mode. And then basically the other one that is most important is ability to optimize your tape motion. Tape is 1,000 meter long, 472 some reps, for instance, okay? And you're gonna write this thing or read it, and if you are not careful, if you don't have the right system and right infrastructure, buffering and all that stuff, then you're gonna write, let's say, and I'll talk about LTO 9, 18 terabyte data to a cartridge. LTO 9 has 280 reps, 1,000 meters, 280,000 meters. You look at the end of your writing, you went million meters. It's real. What's your efficiency? 280,000 divided by 28%. Okay. That means you did a lot of waste motion. What does that mean? If time, transfer rate, more important, tape wear, head wear, debris generation, drive getting dirty. Now you got to clean the drive. You don't know it happened. You're going to write, you're going to have accelerated errors. Here we're above 90% of tape efficiency. That's very important. This is like key to success in a way. Next slide. Some more performance data we wrote. This is from an actual ActiveScale system, physical system that I monitor because I want to know how these systems behave, not just the user has, like he's writing, reading his data. I want to know how well he's writing, how well he's reading, what is tape efficiency. They don't know that, but we get the data in the background, we analyze it. Well, here he had 5 libraries, 3 drives per library, rails, redundant array of independent libraries, and using the 2-dimensional EC. And basically, we wrote and read 1 petabyte of data. We read everything. I don't rely on tape doing read after write because you got a wide track, narrow reader. Where did you verify? All it's doing is making sure defects are managed. I have to verify. Why? Fixity check. You want to make sure you wrote the right data. How do you do that? You got to go read it. Yes, it takes twice the time. Sorry. The system does it for you. And you can see that we read it. And basically, transfer rates were, again, so basically in here, what I'm trying to say is tape management, drive management, making sure your soft errors are minimized, and errors are randomized as much as possible is very important. Next slide. Boy, oh boy. Goes back to what I said. You want to be a tape expert, just ask any question, check your environmental. But here's a good example. The gray box saw in there, this is an Ashrea spec, but the LTO spec says the gray box, you should be in there. The application that I just showed you is not exactly in there, it's in the yellow box, okay? So it's not in ideal location, it's off ideal location, but because we managed it, operated so perfectly that it actually runs beautiful. So yes, you can operate this outside, but you have to be very careful, manage it, maintain it, and keep track of what's going on. Our systems basically checks environmentals from all the sensors. And the thing that you want to be aware of, if you're operating at like near 30 degrees and 50% point in the upper corner of that yellow parallelogram, if you have a cooling occurs, okay, you're not changing your moisture content in your system, that thing is going to go all the way to 70, 80% humidity. That could create condensation, or at least microcondensation. Okay, that's when you lose head. So you have to make sure if you have a system like that operating, you need to monitor, check, create alerts quickly so the user can go and do the right thing. Hey, you're getting too cold. Something happened. What's going on? And go check your system. So next one. This is the erasure coding I mentioned. You have file X1, X2, X3, X4, X5, 5 different tapes. We erasure code each file with their own parities, P1, P2 through PM in this case. And then laterally, we add 2 additional cartridges, H1, H2 for each row. So that's global and local parities. So now let's go straight down and one more slide. Next slide, please. Okay, important thing is, if you doesn't matter, copy, erasure code, anything. Don't write all your stuff at beginning of tape or end of tape. I mean, it's just like shooting yourself in the foot. Okay, that's like, oops. You're saying 11 nines. Okay, you're saying 30 years, 20 years, whatever. That's a no-no. So we don't do that. We rotate the whole thing. It just gets intermingled. Next slide. Okay, I have 5 tapes. Previous cookie cut example. I got 5 tapes, 2 parities. I got these errors. And I'm going to read my files A, B, C, D, and E. So I load my 5 data tapes. I don't load 7 tapes. No, I don't need them because every tape is local parity. I said, okay, I'm going to read them. It reads the tapes, 5 different drives, 5 tapes. File A gets corrected. 1 parity, 1 failure, 2 parities. Bingo. File B gets corrected. File C fails. File D corrected. File E fails. So you send file A, B, and D to the user immediately. I mean, you got your data. The other 2 files, you go read H1, H2. Now you go across to correct that. That's it. You never need to load copies or anything. I mean, in this case, each tape would have a copy. You would have 14 tapes to deal with, and you don't. So that's it. That's the concept, the 2-dimensional erasure code. Next slide. It really works. This is before the ActiveScale project. We did that. I had to repeat the same project to make sure it's done. We wrote data, and we took the magnetics off in this thing. The other one, we cut the tape and scotch taped the tape, and the drive fails. I mean, without the ECC correction, the drive fails. Same thing. What happens is drive goes and fails there. We tell them to go back, jump over that section, read the rest, and boom, it works. The guy that did this for me, he was a soccer player, and Shohab Arslan, he actually put Juventus Pirlo's soccer famous penalty kick, and he goes, look, Turguy, we can still watch it. I said, amazing. So that's basically what the technology is.
In all the presentation, there was a data collection. There was a slide about data collection, all about statistical data.
Yes.
Do you obtain that from the customers, or do you internally? Obviously, you have internal data for your own developmental analysis purposes, but do you also seek to obtain that from customers? And how do you do so? How do you get their consent to agree to give us that behavioral data of the drug?
So it's years old, and for our ActiveScale, we basically collect. Yeah, I mean, there's certain areas that you can't get information, but for our ActiveScale customers, we basically tell them, hey, we want to collect. This is a format, and it's an open format, so we like to get to.
Can a customer potentially refuse to say, I don't really want to share it?
If they say, then it's there.
So in other words, the drive always is collecting these statistics.
It's an open data. If you go to the web, look at the SCSI OEM document, it tells you there exactly what the data is.
Kevin Bracey, what interface do you use to connect to a PC? Like when I say what interface I mean by that is, you mentioned SCSI, but SCSI is 20 odd years ago.
Well, it's a SAS connection. SAS, there's Fibre Channel, that's it.
I showed this slide with the different tape errors. Then was it all combined or
Different, like one with the eye chart.
tape alerts versus drive tape error
Oh,
matrix?
LTO 9.
So everything was taken now.
So you were talking about the tape getting thinner. Is one of the error issues having to do with whether there's write through anymore, or that's not a problem anymore? One layer of tape causes a chip signal in the next layer.
Good question. Yes. Pinholes, for instance.
But that'd
Yeah, like as the thing gets thinner and thinner, magnetic coating ges thinner, the backside feeding into the front side, then all of a sudden you see backside roughness in the front, and then that causes us errors.
it's still a problem.
Oh, absolutely. That's where the coating magic and backside and front side coating magic, smoothness of the substrates is very critical. Any questions from the Zoom side? It's very reliable. Don't misunderstand me, because as much as I said, this is like still the errors are extremely low, 0.001%, something like that. I think it's important to know your system, know your conditions, and deal with each one of those applications in that specific manner.
You explained your erasure coding, how you make good error rate.
Yes.
But so other tape libraries, they do it in a different way and they get the similar results, or you're saying only with erasure coding you get the
I
design?
think erasure coding, well, first of all, it was invented by the Berkeley professors here back in 1980 or something. And then became RAID, and then RAID 5, RAID 6, and then object store and everything. But even all those years, 20 plus some years, we still use copy. Lately, there's been some discussions on erasure coding, and you can use either what we're doing, or you can use like something like this, or you can use striping across the tape, or you basically write two tapes and then you parity tapes. Okay, not stripe. Striping is some difficulties, but you don't have to stripe. So if you just take five files, dump them individually, 5 different tapes, and then go and generate parity tapes from that. Okay. The thing is going to be is every time you have an error on those files, on those individual tapes, you have to go get 7 other tapes. Well, so it's going to impact your availability, not necessarily your durability. There's two things there: availability and durability. And that could become an important, although there's many other things could affect availability, but it's only part of the equation. Thank you very much, everyone.